the theme today being binary search, meaning you make a decision based on going halfway and making an educated guess, going halfway in your array, and then going another halfway, and depending on where you land in the array, you make the decision if you go left or right, guaranteeing that you have at most like logarithmic runtime in accessing the element that you want to access. Let's have a look at a couple of problems and how we can use binary search to solve those problems, as they are just variations of the theme binary search. First one here is 162, find peak element flagged as medium. A peak element is an element that is greater than its neighbors. Given an input array nums where nums I not equals nums I plus 1, find the peak element and return its index. The array may contain multiple peaks, which is expected. In that case, return the index to any one of the peak is fine. You may imagine that nums minus 1 equals nums n equals minus infinity, like being like the opposite of a peak, as opposite as possible. Example 1, input equals nums equals 1, 2, 3, 1, with 3 apparently being the peak. So output array position 2. 3 is a peak element and your function should return the index number 2. Example 2, input nums 1, 2, 1, 3, 5, 6, 4. So 2 and 6 apparently are peaks, so we need to return those index positions. Output 1 and 5. Explanation, the function can return either index number 1, where the peak element is 2, or index number 5, where the peak element is 6. Okay, next problem is square root of x. Implement square root of x, int x. Compute and return the square root of x, again as an integer, where x is guaranteed to be a non-negative integer, so we are not dealing with any complex numbers. Since the return type is an integer, the decimal digits are truncated and only the integer part of the result is returned, which is key in order to solve that with binary search. Example 1, input 4, output 2. I think that's something you can still compute in your head. Example 2, input 8, output 2. The square root of 8 is 2.828242 going on forever. And since the decimal part is truncated, 2 is returned. Next example is number 222, count complete tree nodes flagged as medium. Given a complete binary tree, count the number of nodes. The definition of a complete binary tree can be found as follows. In a complete binary tree, every level except possibly the last is completely filled, and all nodes in the last level are as far left as possible. It can have between 1 and 2 to the power of h nodes, inclusive at the last level h, with h being the height. Example, input 1, 2, 3, 4, 5, 6. And then what we want to do is count the number of nodes. So we count 1, 2, 3, 4, 5, 6. That's 6 nodes. And the last one, flagged as easy, 374, guess number, higher or lower. We are playing the guess game. The game is as follows. I pick a number from 1 to 10. You have to guess which number I picked. Every time you guess wrong, I'll tell you whether the number is higher or lower. You call a predefined API, guess int num, which returns 3 possible results, -1, 1, or 0. -1, my number is lower. 1, my number is higher. 0, congrats, spot on, you got it. Example, input n, pick 6, output 6. So that are the 4 problems. pertaining to binary search. Let's have a look at how binary search actually works in detail, and there's like a really good description this time from Khan Academy, and they even refer to the guessing game as a really good example for the binary search. But even more interesting as a motivation is like the fact to just like really be able to fast browse through a gigantic catalog. For example, here the one with the stars in the galaxy, where you have over 2 million stars, and with binary search you would not have to query more than 22 times, which is the logarithm of, or like the exponent 2 to the power of 22 would yield you that number, the upper bound for that number. So you're guaranteed within 22 searches to actually have found the exact star that you want, which is pretty neat. So binary search really basically works by finding like a mean value between your ranges, the lower and the upper range, and then you go into that value, search there, and query if your new value is basically higher or lower than the desired value. Like if you have a sorted array, say going from like 1 to 10, you don't really know which numbers are in there. You just go like halfway point. What's the number there? And maybe if you look for number 5 and you encounter number 7, then that means you have to search in the first half of your catalog of your array, right? Because it's lower. So you search again for 5 halfway points, so like the first 2 elements and the last 3 elements. You look at the halfway point. Is this still larger than 5? Maybe you have encountered a number 2, so then it means no, it's not larger, so you have to search in the upper half. So you search in there for the next elements, again like logarithmically, divide the length by 2 again, search for the mean point and see if that's the value. And let's say for the sake of argument you have found exactly the value, then you're done, because you've basically found your terminal condition, that is finding that exact value in your array without knowing too much about the array, except for the fact that there's an ordering going on in the array. That can be tedious, specifically say if you know you're only like a couple of numbers away from your target, and you still like half divide your way up to it, when you could basically just like do some iteration, just going straight forward, like from your current point, just iterate a couple of numbers forward to see if you just like hit the number. So with the interval being smaller and smaller, at one point it might make sense to just like iterate a little further. But with like gigantic intervals, specifically with those intervals of millions, just half divide your space and be sure that your number is not part in one half of that array is already a big time saver. So with that in mind, let's look at the variations and how our theme has been implemented in order to solve those variations. Find peak element in an array and have a look at it. So what he's doing here is basically really implementing this find a low and high mark and divide it by 2 to get like a new midpoint, and then query that midpoint. So first of all, make sure that the index of the midpoint, so we're talking about indices for the low and high marks, are greater than 0, right? So like we've never been out of bounds on one end, and so you're always greater than 0. That's one thing. And then the other thing is like, are you with your element smaller or bigger? If you're bigger, then that means you're actually like closer to having an actual peak going on, right? If you're smaller, then that means you're just like going into a valley, which means in which case you actually should have to go cutting your range into half. And that's exactly what he's doing here. So like from one midpoint, he's just going to the left, and he's like focusing only on that left half, and see if in that half range from valley point to left peak point, potential peak point, do I find a peak in that range? And he's doing exactly that, right? And then in the other case, if the middle case is smaller than the next element, you will have to search on the right half. And in any other case, if your range has decreased so far that low and high are either equal to each other or have flipped, like high is on the other end of low, then you have to return 0, meaning that you don't have an element. But in the other case, if you found like a midpoint, and it's that midpoint is basically higher than the previous element, then you have found the peak. Okay, so here's a very interesting solution for the square root, basically tackling it from the other end. You want to search a value whose square is just below, and then the next square is just above the desired value whose square root you want to take, right? Because we are talking about integer values, it doesn't really matter to find the exact square root. It just matters to like find one integer whose square is lower than your original input value and whose next integer is higher. And that's exactly what you want to do. You also know that your square root has to be smaller than your original input value, quite likely. So you can make some educated guesses on where your upper and lower bounds are. Here, he's actually initiating the lower bound to 1 and the upper bound to the value itself. And then while the lower bound is still smaller than the upper bound, while left is still smaller than right, and we have not crossed, we will proceed and do our midpoint search. So we take value 1, or like position 1 left, position 2 right, get that value and divide it by 2 to get at our new midpoint. And we check that midpoint. Hey, is that the square of that midpoint, is that larger than our square? Quite likely with this definition, like how we start. Then we will have to adjust our right or our high mark to that midpoint, and then only search from left to new midpoint. Otherwise, we search from midpoint to right. In any other case, we will return the midpoint. So if the resolution is exact, if the result is exactly a square, like in the example of 2 and 4, we will likely end up getting actually to the value 2. We just straight return 2. In any other case, we will check with the last remaining integers, who are then just like basically neighbors of each other. We will check then if the right neighbor is smaller or equal than the target value, then we will return exactly this one. In the other case, we will return the left neighbor. So it's like either my right neighbor is still, the square of it is still smaller than the final value, or the left neighbor's value is smaller. And since we're like kind of truncating all the digits behind the comma, and only looking for integer values, it's really only about finding that candidate out of the two candidates, my left and right bound. Next up is binary search in a binary tree, and we wanted to count the tree nodes in the binary tree. And sure enough, also here we find the same concept where we iterate until the left is only one neighbor away from the right bound, or the lower bound is only one neighbor away from the upper bound. And during our iteration we will go midpoint is exactly halfway between left and right, and then we check, does that node exist in the graph? If it exists, then we will only search in the range from left to end. If it doesn't exist, then we know we are already like too far, and we only need to search in between between the original left and between the new middle value. So we are adjusting our ranges and only look in the new ranges. And at one point we have found exactly the two counts that will tell us exactly how many nodes are in there. So it's basically, instead of like really iterating through the entire tree and finding it, we are just guessing a number of how many nodes are actually in there, and check if that number actually exists in the tree or not. And that's basically the whole magic behind using a binary search in a tree deemed being complete. And the last problem we are examining here as a variation of our binary search theme is the guessing game, right? One person has a number in mind, the other person guesses it. That can take forever if your allowed range of numbers is large enough. However, if you do the binary search, you are guaranteed to have like some logarithmic guessing time. So the logarithmic guessing time then is like performed as follows: guess number with input range. So guess my number between 0 and 10, for example. Then a 10 would be assigned to n, and then the lower bound or the left bound is assigned to lower end of the range 1, and then the upper bound is n. And then while lower bound is still lower than upper bound, or while left is still lower than right, do our mid-value thing, right? Left plus right divided by 2 gives the new mid-value, and guess that value. Hey, is it the value? Great, then we have solved it. If it's not the value, then we get the other feedback saying if it's -1, then the number is lower than the guess number, which means in that case we have to go from left to the new right, which is mid -1. In the other case we go from mid +1, which is our new left, to right. So we are halfway in, and then checking, have we found the value? No, then we search in here up until we find the value. And in the other case we search in the other range. And that's basically all to it when it comes to using binary search. It's really just about finding those like starting ranges, left and right, and then go to the midpoint and see where am I in my tree, in my array, in my guessing game, and get a feedback on, am I too far left, or am I too far right, am I too high, am I too low, and based on that feedback I'm adjusting my new guessing point, which is the new halfway point between the current mid value and the left and right value. And this way I'm guaranteed to have like a logarithmic approach to finding the actual value or the closest value, or in that one case finding the peak value.